And basically today is going to be hopefully about saving you guys some time. We're going to go through the Canvas lesson on single and double replacement reactions. And we're going to do a couple of examples. And then hopefully we will have time to actually complete the quiz together so that next week you guys won't have anything to do for chemistry, right? So I thought that would be nice. So I just went through the Canvas lesson, took some notes, added some extra information here. So I'm going to give you guys a couple seconds if you want to get a notebook, if you take notes online, however you're going to do it, so that you can be jotting stuff down. This PowerPoint, of course, will go up on Canvas, so you're welcome to reference it later as well. But I know for me personally, if I'm not writing stuff down, then I'm usually falling asleep. So we're going to describe and define single replacement reactions, describe and define double replacement reactions, identify the types of reactions we see from a few examples, and complete the quiz together if we have time. I think we'll have time, but just in case we don't, I will be offering extra credit on the quiz instead of completing it. So the warm-up question is, what do you think a double replacement reaction is? Just thinking about the words. We also kind of saw this briefly in the last virtual session with the vinegar and baking soda. But go ahead and pop into the chat what you think that means, a double replacement reaction. Oh, good. We got a few other people in here. An element is replaced twice. That's a great guess by Abby, right? We're seeing the word double and replacement. So something is being replaced twice, possibly. There's something going on here twice is definitely going to be key. Okay, good. So we will actually go and define a double replacement reaction. So it's when the ions of two substances change places in a solution. So the key here is that it's not 100% in a solution. There are some that happen not in solution, but most of these reactions take place in a solution, and those ions, right, which can usually only exist in a solution, switch places. So what does that look like in terms of an equation, right? If we look at this graphic here, AY plus BZ will yield AZ plus BY. So in this case, Y and Z are switching places, right? So A and B are positive ions, Y and Z are negative ions in this particular example, and they basically just switch places in a solution. Seems pretty simple, right? It's pretty easy to tell what it is when you get the entire equation, where you can just say, oh, well, look, those two things switched places. It must be double replacement. We're going to be making it a little harder by actually looking at just the reactants and actually predicting the products. So here are two examples of this occurring, and we're going to do some highlighting, underlining kind of stuff here. But we see here aluminum nitrate. Why is this not going away? There we go. And we got sodium hydroxide, right? And we're going to be mixing those two things together. And we end up, we're going to assume getting a double replacement reaction because these are examples of double replacement reactions. But we can trace kind of what happens here, right? So we see our nitrate is going to relocate, to be with sodium instead of aluminum. And our OH here is going to relocate to be bonded to aluminum in our products. Right, and notice this is a balanced equation, right? You can check that yourself, but when we are writing out these predictions, right, of what our reactants are going to be, we will have to balance the equation as we go. And we're gonna have to think about bonding, right? Aluminum has 3 valence electrons. So hence why we need 3 OH groups here. Okay, another example, sodium hydroxide, and I guess this is nitric acid, actually. So this is another classic example of when we do a base plus an acid, we end up getting water and a salt. I know sodium nitrate doesn't seem like it would be a salt, but it is, right? So we end up getting a salt and water. We will look at exactly the other types of things we might see in these reactions in a second. But basically, all you're going to do here is trace kind of what happened. This one is a weird example, right? Because really we only see the sodium and the nitrate combining together, and it seems weird because when you see the hydrogen and the hydroxide combined, it makes water, which doesn't exactly look the same as our first example, right? So keep in mind that when things recombine to make your product, it might not be super obvious that it was a double replacement reaction, but these acid-base reactions are always double replacement reactions. So many things can happen here when we see these reactions in terms of what we actually visibly see. So the first thing that we might see is a precipitate, can't speak, precipitate, which is a solid that doesn't dissolve. So you guys might have seen this in examples, videos. There are some videos in the Canvas lesson that I recommend you go check out if you're interested in it. You could also Google this to see other video examples, but basically when you mix things together, you will actually see a solid form and it looks like it's raining inside the solution, right? This happens because whatever solid is formed doesn't dissolve well in water. So it becomes a solid because it can't dissolve, and it just basically falls out of the solution is what we end up seeing. So when we see real full equations written out, not only are they balanced, but we also would see these parentheses of what state that element is in. So AQ means aqueous, which means that it's dissolved in water, right? And S means solid, L means liquid, and G means gas. So those three are pretty obvious and standard. So here we see we have two substances dissolved in water, and the production here, the products, we end up getting a solid. And in our solid, that would actually precipitate out of the solution. It's so tempting to say precipitation, but it's not the same thing. So be on the lookout for that, right? Because that's also a sign that this is probably a double replacement reaction. Again, this one's pretty obvious, right? We can see exactly who switched places here. So in more advanced chemistry classes, you can actually predict which substance would be a solid by using solubility rules. We're not going to be doing that. So you're not going to be responsible for knowing, oh, well, silver chloride would become a solid. How are we going to know that? We wouldn't, right? So not super important to know those solubility rules yet. We could also see formation of a gas, right? Which is usually a sign that a reaction is happening. However, that precipitate could be a sign as well. So in this case, right, you would see a gas in your products, and not everything would be aqueous. I'm having a hard time talking today, guys. Oh, I need a break. Okay. So here, right, we actually see we have an acid, but we also, in this case, are interacting with a metal. Usually when you have a metal and an acid, you get gas. Something that you'll just kind of pick up on after you see it many times. But again, here we can see two things switched places. We're left with a gas. Tells us that a reaction happened, also tells us double replacement reaction. You could also get formation of water. And this is what I was mentioning before. When you mix an acid and a base, you get a salt plus water, right? So one of the most classic examples here, hydrochloric acid and sodium hydroxide, we mix those two things together in equal amounts, we will get table salt and water. And notice here, right, water, we just abbreviate it with a liquid. It's not in a solution because it is the solution. And this salt will dissolve in water, right? So it is in solution. This is actually how you can clean up spills. So if you ever spill an acid or a base in a lab, you pour the opposite one on and you end up getting a neutralized substance. So if you spilled a base on the floor, you could pour an acid on top of it, assuming you know what base it is and how much it was approximately, right? And then you'll end up just having water, and then you could easily just wipe it up. Because if you try to wipe up a base, it's gonna, depending on how strong it is, it might burn through your towel, your hand, etc. So good safety tip there, right? So we could see the formation of those three things: water, gas, or precipitate. Okay, so that was double replacement reactions. They are actually first because they're kind of simple, right? We really don't see too much craziness going on with them. Single replacement reactions sound like they would be more simplistic, but we actually are going to be able to predict whether they can happen or not. And we're going to use something called the activity series here to do that. So in a single replacement reaction, going off of what we know about double replacement, we're assuming, okay, one thing is going to switch places. So in this case, our example here, we have lithium, just the element lithium by itself, interacting with zinc chloride, right? Lithium will take the place of zinc, and we end up getting lithium chloride, and zinc is left by itself, right? That seems pretty simplistic. One thing is switching places with another. Okay, nothing crazy. However, what we're going to learn is we're going to be able to look at this element that's by itself, and based on its reactivity, we'll be able to predict whether it would be able to take the place of zinc. Because remember, it's having to break a bond and wedge itself in there, which is not going to happen in every situation. So some of these might actually result in no reaction instead of resulting in products. And that's something to keep in mind, that we might actually end up not having a reaction at all. So how do we know, right? Well, we use this thing called the activity series, which I 1000% recommend you either write in your notes, print out, add to your notes. There's a whole bunch of different examples of this. I just took this one from Google Images. But basically, this one shows by decreasing activity. So at the top are the most reactive. So lithium is the most reactive metal, right? And then we go down here, gold is the least reactive. For halogens, we have chlorine being the most reactive, followed by fluorine, bromine, and then iodine. So we use this table to actually see if something will react. So if we're looking here at our first example, we have AU. What does AU stand for? You can use a periodic table if you need to, but what is AU? AU is gold. Thank you, Janie Mae. So we have gold, and we're trying to see if it will react with zinc chloride. So all we do is go to our activity series and look. Is gold higher up than zinc? No, right? Zinc is pretty high up on the activity series. Gold is really low. Gold basically will not ever take anyone's place. So in this case, there would be no reaction. Zinc chloride is not going to get broken up by that gold, and all you do for that is you literally write no reaction. Whereas if we have the other situation where we have zinc interacting with gold chloride, right now we see, well, zinc is higher up on the activity series than gold. That means that zinc could take the place of gold, and it does. So our reaction would happen, and we would end up getting zinc chloride plus gold. So this is a reaction that can't happen both ways, right? You guys might have seen or started to notice that as we get into some of these reactions, sometimes you'll see arrows like that, right, where the reaction could go both ways. This reaction can't, right? This reaction can only progress if zinc is taking the place of gold. Otherwise, it can't happen. Okay. So here's a more advanced activity series from Canvas directly, right? So if you go into this lesson, you can actually get your own copy of this. I tried to make it as clear as I possibly could. But basically, it's the same kind of thing that I showed you before. You might even want to have both kinds of activity series in your notes, no reason not to. But basically, this will tell you, right, whatever's on the top is going to take the place of the other metal or element, you know, unless it's like gold, in which case it's never going to do anything. So this kind of gives you some more details too, where in an acid, these things could replace the H in an acid. They could replace H in H2O, and they could replace less active metals. So the example that we just looked at was less active metals, but the H in acids and the H in water can also be replaced by these metals, right? Same with these metals. Same with these metals. And then finally, we get down here where we see that they're not very reactive, but they can still replace less active metals, right? But these last ones down here, including hydrogen, right? Hydrogen is on this list. Hydrogen will replace, for example, all these metals below it, but these metals will not replace hydrogen in an acid or water. So this is one of those situations where if you don't have the activity series and you're not looking at it, you're going to get these wrong, right? There's no way you're going to have this completely memorized. You'll probably know lithium is the most reactive, right? Otherwise, you're going to need to reference this activity series. So you want to have one printed and ready to go. So let's try to predict. Whoa, I wrote predict the reactants. I meant predict the products. So let me fix that. Okay. Predict the products of these reactions. So you're going to need the activity series open. In fact, I'm just going to paste one right there. And we're going to we'll do the first one together. And then we're going to take a couple minutes to see if you guys can figure out some of the other ones. And then it looks like we're going to have plenty of time to take the quiz together in Canvas if you'd like. So first one, we have zinc and we have hydrochloric acid. So we're going to come over to our activity series, right? Because this looks like it could possibly be single replacement reaction because we only have one element by itself. We look on our activity series, we find zinc. Zinc is above hydrogen, right? We could also refer to our other activity series where we would find out that zinc does replace the hydrogen in an acid. So what does that mean? We will get ZnCl plus we'll get hydrogen. Now, we need to balance this equation, right? So, to balance this, we need to think about the bonding between zinc and chloride. Does anybody know the valence electron for zinc? Or have any idea of what our subscripts should be here? And if we don't know, what could we do? Well, we can Google it, right? To see what the valence electron of zinc is if we're not sure, right? Valence electron of zinc. We got our configuration. Let's see, let's find a actually good source here. Homework help, no. Oh, this isn't good. These are all terrible, terrible sources. But I'll just tell you guys, the answer is 2. There's 2 valence electrons in zinc, which we probably could have gone through some of those websites and saw that. Most metals have 2 valence electrons, although there's some that have 3, right? So you might want to check where my PowerPoint go. Okay, so we have our zinc chloride and our hydrogen. What we do know then is that, I'm going to erase this actually so I can put it in correct form. We know then that we're going to have Z and Cl. We're actually going to have 2 chlorines bonding with our zinc, plus we're going to have 2 hydrogens, right? Because hydrogen has 1 valence electron, it's going to need to bond with itself in order to actually exist, which means that in front of our HCl, we're going to need a 2. Okay, give me a 1 in the chat if you are following along, understanding what's going on. You're like, okay, this doesn't seem too bad. Give me a 2 if you're like, I have no idea what we're doing. Okay, we got some 1s. Okay, good. We got a lot of 1s. Okay, good. Just making sure. We got a 1.5. All right, that's fair. Right, so all that we did here was, the new thing is looking at this activity series to figure out if this reaction will even happen. And then we're building off of previous knowledge here, where you actually have to figure out what compound would be formed, and you also then have to balance the equation. Right, so there's many, many steps. First, does the reaction happen? Second, what compound would be formed? Third, balance the equation. So the balancing was easy. I just had to put a 2 over here to get my 2 hydrogens and my 2 chlorines, right? But I had to think about valence electrons for zinc in order to figure out how zinc and chlorine would bond. Okay, so let's try, we'll do the second one together too. No reason to not do a million of these together. So we have magnesium, and we have, is Ba barium? I think so. Chlorine, right? Always good to have a periodic table open too. So what do? We pop over here to our activity series. Magnesium is really high up on our list. I don't see Ba, right? So I might go to the more complex series for a second to see if Ba is on there. Oh, it is. Okay. So Ba is very high up on this activity series, higher than magnesium. So what does that mean? That means that magnesium will not replace barium here, and we will get no reaction. You guys are going to like when there's no reaction because it's the least amount of work. You just write no reaction and you're done. Okay, so all I did was consult the activity series. Again, this is like a condensed version, so it doesn't have every single one. If you don't see the element that you're looking for, right, then go to the more complex activity series that has everything listed and make sure that barium is not below magnesium and it's actually above, so no reaction. Okay. Third one. Does this look like it would be a single replacement reaction or a double replacement reaction? Abby says double. Yeah, it would be double. Right? So I want you guys to try to figure out what compounds could form if this is a double replacement reaction. And how do we know it's double for those of us who are like, because we see 4 elements here, right? That means that they could switch places. This could not be a single replacement reaction because we don't see a metal just chilling by itself. Okay, so take a second here. In fact, I'm gonna stop sharing my screen for a second because I'm also gonna do this. If you finish number 3, try number 4, right? That's also a double replacement reaction. See if you can figure out what those compounds would be that get produced. Oh, I just realized you guys kind of need to see them, don't you? Here, let me put them in the chat. Sorry about that, guys. I didn't think about how if I take my screen share away that you actually can't see the reaction unless you wrote them down, right? So those are the 2 that we're working on right now, number 3 and 4, trying to figure out what are the resulting compounds of these double replacement reactions. Okay. And when you have finished both of those, just pop a 1 into the chat, right? And feel free to take your time. Remember, the hardest part here is going to be figuring out that bonding. When those elements switch places, right? Make sure that you're thinking about valence electrons, look at that periodic table, really determine what the bonding will be. And again, when you're done, type a 1 into that chat. I'm going to give you guys more time. I'm going to use the bathroom really quick while you guys are continuing to work. Ow. All right, type a 2 in the chat if you'd like for me to start going over these. Okay, even if you didn't quite get it, maybe you did part of it, you want to know if you're on the right track. Right, keep in mind, guys, this is hard stuff. We're going from basically knowing, oh, this is a double replacement reaction, to actually writing out this entire equation, right? And using all of our knowledge from the whole year, pretty much up to this point. So if you're feeling like this is hard, it is, right? And it takes practice, and then you will become much better at it. So we see here that we have copper, a chloride, we have some kind of acid here, right? We have an H in front with sulfur, so hydrosulfuric acid. And we want to figure out what happens. So the first thing is to just type out what we're going to end up getting. In this case, it looks like our copper is going to go with our hydrogen or our sulfur. What did you guys think? Yeah, the copper is going to go with the sulfur, right? Which at first you might not have seen that, right? But we're going to end up with CuS. Plus, we're going to get our chlorine and our hydrogen bonding together to get a hydrochloric acid. So what's interesting about this, right, is interesting, but also makes sense. We started with an acid, we end with an acid, right? Because the acid is still there, it's just switching the type of acid. So now we want to work on bonding and thinking about how these things work. So HCl, that works. Hydrogen has 1 valence electron, right? Chlorine has 7, so those two will bond together. And then what about copper and sulfur? What is our valence electron for sulfur? Abby says 6. Good. And copper is a metal. Its valence is 2. Right? So that actually works out. Copper and sulfur bond together. We don't need any subscripts there. However, we do need to balance our equation now, right? We know that these two would bond. Great. Well, if we look over here on the left side of our equation, I see 2 hydrogens and 2 chlorines. Here I only see 1, right? So that's a pretty easy one. We're just going to pop in a 2. Sorry that my finger mouse pad writing is ugly, but we'll end up with a copper sulfide and a hydrochloric acid with a 2 in front of it there, right? So then our equation's balanced. We had a double replacement, both things switched, right? So that one works. Okay. Our second one is a similar kind of situation, except this time there's no acid. We have a potassium carbonate and we have a calcium chloride. And we want to figure out those switches. So the first step, again, is just to switch them. So we're going to end up with calcium with this carbonate on the end. And we're going to end up with our potassium and our chloride. And literally all I do the first time I look at this is I just switch the places of the elements. Then I'm going to work on bonding. Okay, so let's start with potassium. What is our valence electron for potassium? It's 2. And guess what? Our valence for calcium is also 2. So that's awesome. Well, maybe it is. We'll find out. Because that kind of means that when they switch places, it sort of just works out perfectly here, right? Our calcium, wait a second. Potassium is 2 or 1? Let me look at the periodic table. You know, every week when we do this, okay, there we go. That's what I thought. I was about to say. So this is why the periodic table is 1000% necessary to look at, right? Potassium has a valence electron of 1. Okay, so that's going to actually work out nicely for us, but not in the way that I was thinking. Okay, so then when we look here at our potassium chloride, well, guess what? Chlorine has 7, right? So to bond with that potassium, that works. Okay, what about this carbonate? The CO3 grouping. What is the valence needs on that, or what is the charge on that ion? And again, if we don't know, we can always look at our polyatomic ion chart, which again is something that you should print and have in your notes, right? There's a million versions of it. But we're looking at CO3 carbonate. It has a -2 charge, right? Calcium has a +2 charge as an ion, right? Or a valence electron of 2. So those two will actually bond together as well. We don't need any subscripts here. So this is the perfect switch, okay? And guess what? A lot of these are gonna just work like that. But now we need to balance, right? Because the equation is not balanced. So we wanna look at, we have 2 chlorines and we have 2 potassiums, 1 carbonate, 1 calcium, so that looks good. So we really just the similar concept to above, we need to put a 2 in front of that potassium chloride. And then our equation is balanced. Okay, last example that we're gonna do together. Actually, you guys try number 5 first really quickly. This one should be a little quicker than the double replacement reactions, which take time because you really do have to look at that bonding. We're looking here at sodium and magnesium, and we want to know, will that reaction happen? And if so, what will happen? So you may, actually no, this activity series here over on the right can be used here. So first question, will the reaction happen? Let's check. Is sodium higher up than magnesium on the activity series? Yes. That means sodium is more reactive. That means sodium will take the place of magnesium. So this reaction will happen. Great, now we have to figure out what it is. Well, we know the sodium and the magnesium are going to switch places. So we're going to get NaCl, and then we're just going to have that magnesium by itself. Okay, magnesium by itself, that's fine. Sodium and chloride, they bond perfectly, right? Because sodium has a valence electron of 1, chlorine 7. They form nice ions that way. Now we just need to balance. So looking at our left side of the equation, I see 2 chlorines. Here I only see 1, so we definitely need to put a 2 here. And then that means we need to put a 2 in front of our sodium on the left side as well. So we have 2 sodiums on each side and 2 chlorines on each side. So that looks beautiful, except for my 2s, which look ugly, but they're all right. Okay, so then that would be our final equation there for that reaction. 2 sodium plus magnesium chloride yields 2 sodium chlorides plus a magnesium. Okay. That took a long time to go over that. So now I'm not sure if we're going to have time to do the quiz, but I also think you guys should do some more practice on this. So I'm going to show you where you can do more practice, because honestly, this type of work, really, the more you do it, the easier it's going to get. right? And the more you're going to be like, oh yeah, that's how this works. So what you're going to want to do is, first of all, I will tell you the code word for today is in the chat. You can get 3 bonus points on any assignment that you'd like. I say add it to the quiz, but if you'd like it on a different assignment, that's fine. So keep that in mind. All you have to do is put the code word in the comments, or if necessary, you can email me and say, hey, I want my code word added to this quiz, right? And then I'll add your points for you. But if you want more practice here before you take the quiz, which I highly recommend that you do more practice, definitely, you're going to want to go into Canvas, into this assignment, or excuse me, lesson, which is called, what is it? It's not called Module 4 Reactions. Oh, here we go. Chemical reactions, double and single replacement, right? I already took you through pretty much everything on page 2 and page 1. You're welcome to go back and look at that stuff. But on this practice section here, right, this is where I got the first 5 that we just did together. Well, there's another 5 here that I recommend you try, and then you can click check your answers and it'll show you your answers, right? So there's the first 5, the ones that we already did, so that you can check to make sure that your answers are correct. Then there's also another practice, right, where it's a little interactive quiz type thing that I would also recommend doing before you take the quiz. Okay, and then otherwise, we're going to end this virtual session. You're welcome to work on the quiz or the extra ones right now. Or the other option is, if you guys would like, we can do 6, 7, and 8 together right now, if you'd like. So let me know in the chat, do you want to go over 6, 7, and 8? Or do you want to just end the session and you're going to do it on your own and practice on your own? So I guess type together or on my own in the chat. And if I don't see anything, I'll assume on my own is what you guys want. And no one's talking to me. On my own, thank you, Nathan. Okay, Nathan has decided for us on my own, right? If you get stuck on any particular one or you need an explanation for why something is the answer, right, then feel free to send me an email and say, hey, I'm confused about this. And I'm happy to explain it to you or walk you through the steps, okay? Otherwise, I will see you guys next week.